I'm Josh Hobson. I'm the lead rendering programmer at Santa Monica Studio. For those of you who don't know, it's a first-party PlayStation studio responsible for the God of War series. And today I'll be talking about the indirect lighting pipeline from God of War 2018. So the artists were nice enough to provide me with some screenshots from the game, some examples of what we shipped. So first things first, the talk is intended to be concepts and motivations and some technical deep dive. And where possible, I'll work in dates and sort of situations that drove the decisions. It's not meant to be a deep theory talk, no code, no instructions for implementing. And while I do think we bring some new ideas to the table, it's largely based on existing work. So a bit of the boring stuff. Since our game is playable from end to end with no load screens, we don't have large discrete levels. We have what we call WADs that are composed of sort of overlaid Maya files since we're a Maya studio. And WADs are our streamable unit. They are connected together by what we call ref nodes, which is how we implement our prefab instancing behavior, as well as how we subdivide our WADs for workflow purposes so that artists and designers can work in the same level at the same time. Ref nodes can be recursive as well. And it just illustrates that we're always sort of on a conveyor belt loading ahead and removing behind us. So at our first playable around mid-2015, I just realized I didn't start my timer. Anyways, we had an indirect pipeline centered around light maps and loosely placed diffuse probes, which is not an uncommon solution, but it does come with some trade-offs. Specifically, there's a visual disparity between static and dynamic objects that has sort of an effect like the old Scooby-Doo cartoons where you could tell something is about to move because it's in the animated layer and just doesn't quite look grounded. Additionally, this was complicated by the recursive nature of our ref nodes. There's a complex pairing of light maps to instances. An object can be on a an object can be on a table, and then the table can be instanced multiple times in a house, and then the house can be instanced multiple times. So it sort of explodes. And UV unwrapping and probe placement is a bit laborious. I mean, obviously we can build tools to help with those things, and we did. But we wanted to try something else. So the goal was to reduce the manual overhead, try something different. I had used 3D textures for lighting in the previous generation, so it's obviously affordable. Ideally get a consistent look between static and dynamic geometry. And it needs to work with our load schemes. And I mean, I guess the most important is we have a relatively small lighting team, and we want them focused on making art and not on data management. So keeping it simple, they're just loosely placed boxes in Maya. And inside that box is a collection of 3D textures containing the lighting information. It's all static. And since this is indirect data, or indirect lighting, the voxel resolution can be actually quite low, as much as, or even more than 1 meter per voxel at times. The encoding is pretty simple. It's just 2-band circular harmonics, 4 textures. RGB contains the bounce lighting, and alpha contains the sky visibility and monochromatic bounce. So simple test scene, and an example of a few slices of what that texture might look like. Again, bounce lighting on the left, what looks like AO, but it's actually directional on the right. Then the actual sky lighting itself is joined at runtime. We generate a circular harmonic encoding of a cube map that we use for sky lighting, and that is simply multiplied at runtime. We do things like animate the intensity of that thing and rotate it dynamically at runtime as well. When we go to apply these, we on the CPU, we just grab the 4 closest GI volumes that are on screen. And we sort them by an artist-authored priority so that they're stable. They don't pop as the camera moves around, other than during WAD loading or unloading. And this scheme works pretty well for the GPU because it's very dumb. It just walks the list in order and stops at the first one it hits. As I said, the voxel density is low, so there's, as you might expect, self-occlusion issues, light leaking issues. We were extremely motivated to stay with hardware filtering. I know that a lot of similar techniques tend to do unroll the filtering themselves. That can really back up pretty badly, so we wanted to avoid it as much as we could. So instead, what we do is we take the surface normal and we offset it before we sample the GI, so that we're sort of inflating the object out of itself. And there's an example of how that looks. So there are obviously some caveats to that. One is that moving objects get kind of a shiny look that results from a relatively small angular change producing an unexpectedly large visual change. And our minds sort of want to rationalize that as like a reflection vector moving, so it gives it kind of this oily, shiny look. And here's a video. It's a little long and it takes a second to update, so I apologize. So you can see on his arm, it looks very greasy. And then I'm actually recompiling a shader and it loads due to the tiling into different regions first, so that his pelt on the back is updated, or just now updated. So you can see they're much more natural after the fact. Additionally, there is a literal corner case where the normal map normals can quite often point in through objects that are open on the other side. I do believe this can be solved during baking. Obviously, it can be solved by using smoother normals. We really didn't want to allocate an extra set of normals for this problem in our gbuffer. So, but like I said, I think this can be solved during baking by sort of pre-offsetting the sample locations. I did a quick test of it, but we didn't actually ship it. So here's an example of the type of artifact you get, where the normals on the bottom of the sphere poke through the sort of bedsheet thin ground that it's sitting on and sees unoccluded sky. And not the most sophisticated solution, we just cap the bottom of that during bakes, which is not a tremendous amount of extra overhead for the artists. Typically it could be a couple of planes or something just to cover the bottom. And the basic idea is that over-occlusion is more acceptable than under-occlusion. So it does produce over-darkening. When it comes to indirect specular, we have optional screen space reflections, as well as loosely placed cube maps using box parallax correction, which isn't a great fit for the organic environments in the game, but it works okay. It's something that I think we should look into going forward. But there are some downsides, right? You get a ton of light leaking where essentially the GI, relatively speaking, has much higher spatial resolution than the cube maps. And so you get this kind of oily look in the occluded areas. So ideally, we want a solution that works with both. So in comes cube map normalization. And the primary objective is to maintain a natural balance between diffuse and spec. It's not, I guess I'm asserting that it's not so important when the actual contents of the reflections are a bit off, but what's more important, what's more noticeable is the balance, right? So, so ideally leverage the angular detail from the cube map and the spatial detail from the GI. So we generate a spherical harmonic encoding of the cube map during build. And we use that to remove the sort of the low angular frequency data, and replace it with a GI from the runtime. Again, I think this actually helps with the box correction case because it can introduce sort of subtle amounts of occlusion that would otherwise have driven us to use more cube maps. So I think we saved on cube maps on this one, and I think we compensated against the box correction a bit with it as well. So here's a test hallway with a block sort of occluding a corner. You can see the capture location there. Again, from inside the hallway. And so there's the cube map. Obviously, the corner is not visible. And back to the original problematic case that I pointed out. And with it off and then on, you get a much more natural balance. You get sort of partial occlusion. Reflections on one side go in and out of the shadow as you would expect. And I'm going to beat this dead horse. So it's not even obvious here visually that those are actually behind the block until you turn on the normalization. And you get sort of the expected result on that chrome ball where the reflections on the side that's less occluded or exit the occluded area look more natural. I will also point out that this level isn't watertight, so that light leaking in the corner is actually just a hole. So. And again, the greasy wall in the back, which actually has an overhang over the top of it, so it is actually occluded. And again, so. And then to keep ourselves honest, theoretically, if you take a cube map capture and put an object right at that cube map capture location, the GI and the cube map should agree on the contents of what they see, and therefore that divide and multiply should cancel out. So here's an example there. I mean, they're not exactly at the location, but there's no obvious huge shift there. And obviously those little metal tables in the background look much more grounded. So, I mean, this is not an original concept. I don't think we necessarily based it on any particular talk, but it's pretty much identical to the Call of Duty talk that was from 2013. I have heard of studios trying this and then sort of abandoning it and not liking the results they got, so your mileage may vary. There's obviously some issues, divide by zero, and discolorations that result from clamping SH. So our fix for that is just some empirical tuning of that denominator SH so that it avoids hitting zero, which is energy conserving. It just it effectively is like blurring that denominator a bit, shifting more of the signal to the constant term. It's possible that actually using the GI sample from the location of the cube map capture may produce better results than the SH from the cube map, but I think we're doing okay. So there's an example of the type of discoloration artifacts you get, and then with the sort of reduced directionality, which is just scaling down that upper band. So for ambient occlusion, we use obviously screen space AO, AO maps, and character capsule AO, like The Last of Us. And the capture we used ragdoll capsules for those capsules, which worked reasonably well until we narrowly escaped blowing the limit at the end of the game when those sort of competing goals came at odds, where they'd add a ragdoll capsule to fix a popping issue or something, and then suddenly we're out of budget. So going forward, I think we should make a custom pipeline for that one. And here's an example from the forest level. GI only, obviously, and then capsules, SSAO, and then the AO maps. I think the consistency is important, so the volumetric fog actually sees these GI volumes. And around the 2016 E3 demo, we actually went through and re-swizzled all the bakes. They were originally in channel, a map per channel rather than a map per band. So we went through and reprocessed them all so that the fog could just sample only one texture. And credit to Bart that he also exposed that the internal lighting texture for the fog to the particles, so the particles also got both lighting and GI for relatively cheap. I'm not going to go deeply into optimization, but just a little bit here. So it is integrated into our tiled rendering so that every 8x8 tile sort of masks out GI volumes of that set of 4 that are on screen that are irrelevant, and then we simply just do a bit extract with a scalar branch to process only the relevant cube maps or potentially influencing cube maps. And then we also run it alongside of our shadow maps. which doesn't always load balance quite that well, but it's a real capture, so I'm calling that a win. Okay, so how am I doing on time? 50, all right. We actually built the E3 2016 demo, the reveal of the game, using a tool called Nova, which is developed by a shared group inside Worldwide Studios by Sony Research ATG. It was built in the PS3 generation, and it carried over from our light map and probe workflow, which was nice because it was a known quantity, so it was a good starting point. It shipped lots of games, and I do actually think it's still in use now. But for us, we really needed a faster iteration loop than that. So there are a few bottlenecks in that process. One is it has its own data format, which we actually have to sort of build the level into, which involves a rather complex translation of our material system into vertex colors as an optimization. So there's 20 minutes just getting the scene into Nova, and then 30-minute bake. Additionally, it's not always obvious that they've expressed what their model of a spotlight, for instance, is versus ours, and the correct way to translate those. So it does make you sort of wonder sometimes if you're getting correct results out of it. Additionally, thin scattering was a little problematic for us with our material system, and then there was no representation for volumetric fog in Nova. So the lighters already build the game for PS4. We tend to prefer everyone run on the PS4 to iterate. That way we're actually seeing what we're going to ship. So ideally, we want to leverage that build data. We already have a tool set for updating objects or updating transforms and attributes from Maya. And the Nova pipeline was a little brittle for us and largely survived by automated testing alone because it was pretty easy to break it by making seemingly simple changes to the material system. And with only the small group of lighters working on it, it was, it would leave them blocked if it got broken. So we do our baking on PS4. I get asked sometimes why we didn't use a PC build, and I don't know, for similar reasons as I mentioned before, I don't really want them working out of their normal workflow. They're already building data once. I don't want them to build additional data for PC. I mean, PC shares some data, but it's not identical, so it is an extra step. But it also leaves them on an island as pretty much the only group relying on the PC build for their workflow, which comes with a risk that, if we needed to, if the PC build had died and needed repair as the schedule got tighter, it was, I wanted to leave it as an option to say, screw it, we'll pick it up next game and clean it or fix it then, which we obviously wouldn't be able to do. But at the same time, it wasn't roses because there's not that much extra debug memory to work with on the PS4, and there were at least one level that we could only bake on the Neo kits because they had extra memory. I think the Lake of Nine. So the technique is essentially a modified version of the ray bundling technique from Square Enix. Credit to Stephen Hill for his adaptation that we use for GI volumes. Generally, the technique, instead of looping over rays for every point, loops over every point for a given ray. And it does converge on a multi-bounce solution where early rays effectively have fewer bounces. So the first step of that GPU baking is to rasterize, essentially shrink wrap the geometry in the scene into circles, which contain the actual material properties, position, normal, color, etc. And we use the rasterizer to do this. We just don't bind a render target. We don't bind a depth target, no culling, and we just simply use it as go sample a bunch of positions on triangles for us. And then we use a global append buffer to build this big global list of circles. Additionally, we save on build times by hijacking the debug shader, which we already had, rather than adding an additional permutation. I don't know what you guys experience, but shader compilation times are actually pretty long. So adding another shader is non-trivial to build times. So since that debug shader, which we use for visualization like texels per meter, displays, and lots of instrumentation, we just stuffed a scalar branch in there that says I'm baking, so please append what you've already got for the material bake or material evaluation, bake it to a circle instead. So here's the, we first render on X and then Y and Z in this debug mode, and this is going to be the first of many times that I stress how important it is to build good debugging into a system like this, because it is exceptionally hard to figure out what the hell went wrong. Anyways, so again, same view, but now viewing the normals as it goes. After that, we inject the actual lighting into the circles. And again, credit to Stephen Hill for the original technique relied on accumulating the lighting into the light maps, whereas this technique has a persistent set of circles and accumulates the lighting in them directly. So here's our cloud of circles, and then we inject a spotlight with a shadow. And then we progress for a random distribution of rays. For every ray, we project the circles into linked lists, we sort the list, then we walk the list transferring light between neighboring circles, and then finally we resolve that to the in-progress GI volume. So we're slowly accumulating the results as we go, which allows us to actually visualize the bake on real geometry in the scene. So, and do a little bit more depth there. So for every ray, we build an orthographic projection. On that projection is a texture where every texel is a head pointer of a linked list. And we just use a simple atomic swap operation as we're processing circles to hash them. Well, we hash them to their texel, and then we atomic swap them as the new head pointer. Once that's built, then we sort it, and embarrassingly enough, it's a bubble sort. So if my college professors could see me now, bubble sorts and linked lists. Success. All right. It's actually pretty performant, and I don't know. You guys are all game developers. You know that it's all about finding the lowest hanging fruit, and really, it never became a priority. I mean, if it does, we'll speed it up, but it's not shipping code. So again, debug views. So this one, all of these views, by the way, are rendering the real actual cloud of directly from the cloud of circles. This one actually pays attention to the connections between them, and it simply says, well, I expect to be sorted in this direction, and it shows me the ones that are not sorted. So imagine debugging 100,000 linked lists if they're sorted properly. Anyways, and then green means head pointer, blue means tail pointer, I think, and cyan is everything in between. And then the sorted version, everything looks okay. I mean, the columns are pretty big here. That's why you see the zigzagging between those guys, because they're rather large texels. And then here's a debug video. This is real time, by the way, of that debug view as the bake is progressing. And it's actually doing multiple rays in between there. You're only seeing the last ray of the frame. I'll get into that later. Okay, so now that we have that list of sorted, or that set of sorted lists, we need to exchange energy to progress the bake. So we simply look at, actually that arrow is the wrong, or that normal is the wrong color there. That should be gray to signify the surface normal, not the link direction. So obviously opposing circles, they don't exchange energy because they're back-facing and therefore black. Any circle that's on essentially just the head pointer of the list is always sees visible sky, and then accumulates that into a separate component of the circle to sort of propagate the sky visibility inwards. And finally, the last step in the ray processing part of this is to update the GI volume with the in-progress results. And we essentially do the same step. We take the voxel center of the GI volume texel and project it into that same head pointer list and just walk the list until we're between two circles. and then we encode what we see in the direction. And here's a video, again, real time of the progress. Did it start? Okay, there we go. So I think we're to, I don't know, about 200 arrays, and it's pretty representative of the final result. And they can kill those and restart them pretty quickly, but you can see that, in a very small number of arrays, you sort of start getting the idea of what the bake's gonna look like, and you can iterate pretty quickly. So the actual execution of the baker is done with a state machine, and it schedules work by simply inserting passes into our rendering frame. It targets 80 milliseconds a frame so that the frame rate overall stays interactive, but we're spending the bulk of our time baking. So they can still move the camera around and move objects around and rebake and so on. Maya is where they control what objects do and don't participate in the bake, same with lights. They can also assign lights to categories like special effects or cinematics, things that really don't necessarily make sense to be in the bake as they come or go over time, they animate, whatever. They can put them in a category and then exclude that category completely from the bake. They additionally set the voxel density, the ideal voxel density that they want, as well as a guardrail memory budget, so that it will try to respect their density request, but once it hits the budget, it will stop. On the excluding lights from the bake, the 2016 E3 trailer actually had, I think, 3 or 4 different suns at different angles and different intensities because you're progressing through the morning. So all of them were marked as no bake, and we replaced them with one sort of placeholder in the middle. And it worked pretty well. It was pretty labor intensive, I think, tuning wise. So, getting the transitions to hide and all that. So I don't think we really use this a ton in the final shipping game, but it definitely was available. Yep, I think that's everything. So then we also have our own tool that's sort of the front end of the in-game baker on the PC side. It's where the artist controls sort of the context for their bake, which means what additional WADs do I load? You may actually create a load configuration that has more WADs resonant than the actual playable game has for a particular reason, like a GI volume. There's no requirement that the GI volume is wholly contained inside of a WAD, so they can actually have a GI volume that's larger than the WAD, so that neighboring WADs just load in and continue to use its GI. So you may want to include them so that they actually participate in the bake. Additionally, like Vista Mountains or something like that. So they also control how big the area, participating area is here as well. Set the number of rays, surfel density, which for things like alpha cutouts, you may want to control how tightly they fit, because they can get a little bit of over-occlusion if they're very coarse, but obviously bigger surfels means fewer surfels, and therefore it means a faster bake, so they can sort of fine-tune if they want. And then here's where you can choose which light categories you want to disable wholesale. Variable res I'll get to later. So here's an actual production level, hopefully is familiar from the beginning of the game. It's also the troll arena from the E3 reveal. So I'm going to load an additional WAD there for context, and then I'm going to switch over to the ambient view and trigger a bake. And I think we're at 100, 200 arrays, and it's already pretty stable, so 500 was probably overkill. And that's the whole process, the surfel generation and everything. And here is sort of a run through of those debug views I showed earlier. So this is the light component of the surfels, the sky visibility, albedo, and normal. And then I think, yeah, I do a bake in this view from the sky visibility and the lighting. Come on, Josh. I think I'm leaving it till it technically stops, even though you don't see anything happening anymore. And then this one, there's so much contrast, it's really not terribly visible. But you get the idea. We also have single stepping ability in this. So this is that linkless view in a real sort of production environment. Again, imagine sort of debugging all those linked lists. But you can additionally also like step in. There were cases where we had maybe one ray that was had some sorting issues. So you could stop it and start inspecting and live update shaders in the engine to try to fix it and see how that goes. It was pretty valuable. And then I'm terrible at Maya, sorry. So I zoom back and let the bake continue so you can kind of see the overall complexity there. And then lastly, this is sort of the art, my best effort at an artist workflow. So I'll introduce a new object to the scene. And the videos are messed up, sorry about that. You've got a spotlight on this bright red sphere. Switch over to lighting view. Again, I'm sorry about the videos glitching out. And you can see, oh, now that the sphere is in its new position, it puts new circles on there, and then the light exchange continues. That's unfortunate. And you know, when you have a really strong and small light source, you do get sort of fireflies in there. So it might push your ray count up, but generally you can get away with quite a few rays. But you know, pretty quickly you can kind of see the results of your changes, and you know, oh, I didn't intend for the light to get that far down the hallway, so reposition something, move a light around, that kind of thing. I think I have one more that's interesting because you can see the ray directions a little more clearly. Okay. So as I said before, one of the reasons we wanted to move away from Nova was to get sort of more robust feature set inside of the baking. So credit to Bart for this one. It's a modification to his fog technique to basically use a orthographic projection for the scattering and lighting textures over the area that we care about. And then we render a cube map that contains all the fog information for the outside of the volume. So any rays that, you know, escape the area sort of see what the fog would be at infinity. Yep. And then we modify that light transfer stage of the baking to take sort of a fixed world space step, so a variable number of steps, accumulating extinction and inscattering from those textures as we light them. And then the same thing when we resolve the GI as we sample through those volume textures. So here's that hallway again. And then we add a ton of fog. And then what the bake looks like without the fog in it. And then with the fog in there, you can see it is quite a dominant light source. The directionality in that block on the left changes pretty considerably, and a lot more light comes in. Some scenes, it can smooth things out pretty well. Other scenes, it adds directionality. It just depends. And then here's the scene without the fog in the bake, and then with the bake, and it's actually pretty readable even through how thick the fog is. Oops, how thick the fog is. Okay, so we try to support the same translucency model we have for our materials. Again, credit to Bart. So basically, we also add to the circles the translucency color, or the scattering color, and we behave as though the space between the circles is solid medium, and we calculate the propagation or transmission through that. And thin scattering, we do the same thing. The circles are just closer together, and then there's a bit of bit hackery in there so that they always sort in the proper order, regardless of the ray direction. And hopefully that reads okay on the screen, yes. So this is a block of ice that I've sort of juiced the scattering color bright so that it reads okay. And a very bright spotlight bleeding through, which you can actually see the spotlight through the backside of the block. Okay, so a uniform texture is great, and we've got everything working, but ideally we'd like to not waste as much of our samples on sort of dead space, empty air, where the lighting is largely low frequency. And the variations are obviously closer to the surfaces, so we want to sort of redistribute all that texture space over to the surfaces, which might lead you to say, well, I'll just bake a super high resolution and then I'll bring it down, but you'll find that the bake times explode pretty badly, so generally you need something that scales the bake time with the density, ideally, to maintain that workflow. So this is a technique I had done at a previous studio, probably, well, in the previous generation. I won't date myself too much, but anyways, it's essentially a 3D virtual texture. So you have an indirection texture that's roughly 4 meters per voxel. And behind every one of those point sampled indirection voxels is either a 1x1 all the way up to an 8x8. And here's sort of an example of what those textures look like. You've got the indirection texture that's job is to sort of unscramble all that sort of discontiguous blocks of varying resolution actual lighting payload behind those texels. So, as I said, you want the bake times to scale as much as you can with the actual final density, so you need some way of determining resolution requirements up front. And for this, I mean, this was, for some context, this was done pretty late in development, so some of these decisions become progressively less and less scientifically rigorous. So forgive me, but we calculate we do a smaller bake on, say, like 512 rays or something, where we encode at indirection texture resolution the nearest circle, and then we average that over the sphere for all rays. So we get sort of this average across all directions distance, and then we feed that back on the CPU. And start with the indirection texture, assuming that every indirection texel is a 1x1. And then we use a greedy algorithm to decide which, globally for the whole set, which voxel benefits the most, reduces error the most by promoting it to the next one up. And then we continue. So obviously, how do you estimate error? This is where things get a little Wild West, I guess. So my initial thought on this one was, well, if you think about it, if you have a surface with very high frequency information on it, and you move sort of an observing point across it, there's a large angular change as that thing moves because it's close, so why not just use the angle swept by the step size at the average distance of the surface? And it works okay. I mean, it's not perfect for sure, but it was done quickly and worked pretty well for what we needed. Yep, I think that was all I wanted to say there. So here's another debug view of what a uniform GI volume looks like over that same production scene. I don't remember what the memory was on this, I'm sorry, but they are the same between the two. I think it was 30 megs, maybe, I don't know. And here's the variable res version of that. So colder colors are lower resolution, warmer colors are higher resolution, and I'll go back and forth. And to further help with that, I have, again, I'm sorry, I'm terrible in Maya, so my unsteady hand is going to move a plane through this volume so you can sort of see how that changes on the other dimension. So that all that dead space in the top starts quickly and aggressively dropping to lower resolution. Hopefully that makes sense. Okay, so now we know for every indirection texel or voxel what the resolution requirements are. So we need some way of packing it. And with more time, I probably would have found an existing technique that's much better than what I did. But in a nutshell, it's essentially a brute force. We brute force allocate 32 cubed blocks, or sections, not to confuse my terminology here, with these blocks. Pack them as tightly as we can, so now we have a bunch of uniform 32 cube blocks, and then we just sort of treat them like a pooled allocator and just find the best size texture overall to fit them into. And so there's a diagram explaining that, hopefully better than I just did. And then to alter the baking, only the resolve step changes, where we put that data into the GI volume. For the uniform cases, we simply subdivide the scene into 4 by 4 by 4 wavefronts to do the work. Here we do the same thing, except we just go through all the blocks individually as though they were an individual little GI volume and break them into 4 by 4s, which is wasteful for anything that's not a multiple of 4 by 4. And like with the bubble sort, this really never entered into turnaround time, so it never really got prioritized. But we theoretically could try to pack multiples into a wavefront. So as you would expect, we're trying not to unroll our bilinear filtering again. So, and in this case, it would be pretty bad because you'd have to unroll the indirection texture as well. I think I should have put a reference to the virtual texturing slide on there because they do the same thing, but we essentially, well, similar thing. We treat the voxel centers as corners of those blocks rather than the interiors, which introduces a small amount of waste, but it keeps us being able to hardware filter everything. Well, the indirection texture is point sampled, but. So what about seams? Yes, they do happen. They largely happen where you have misestimated the resolution requirements, where your actual lighting payload is higher frequency than the actual sampling that you put there, and where neighbors are of different sampling resolutions. So I'm sort of theorizing that a better error estimator would further reduce these seams. Okay, so and this is another blemish on the system. We read all this back on the CPU, and we use the eigen library to solve those seams. And specifically, we pre-compute the solver for every neighboring pair, so an 8x8 and a 1x1, 8x8, 2x2, whatever. And then we sweep all the blocks on each axis, so X, Y, and Z separately, which means that the corners and the edges are over-constrained, and therefore we have to run the whole process multiple times. So it's a slowdown. It's still significantly faster than the other technique, or the NOVA technique. Yep. So there's an example where you have a block that's obviously not clean with its neighbor, and then after the fix-up, okay. And then to prove that I'm being honest, it's the same debug plane and the same shaky hand, pulling that plane but through the lighting data this time. Hopefully the video doesn't spaz out on me. Oops. Okay. So variable resolution was added in September of 2017. We shipped, or we were gold in March of 2018. That's not a ton of time. Since there was no sort of automatic way to convert the uniform GI volumes to variable res, they became optional and opt-in, which means we had to actually pay for a branch on them. And the artists would sort of pick the levels they felt that they didn't get the resolution they were looking for, or maybe wanted to trim their memory. And I would say that both were probably used in equal numbers, whether visual improvement versus memory savings. And here's an example. I think the normal offset is a little different than I talked about earlier, so there's maybe a larger change than I would expect. But you can see that if you look at that pillar, or the column across the top, there's actually like a block of snow there that's reflecting in the wall, and you can see it's almost not there at all in the uniform case, and you get much more fidelity in the variable res. Okay, so you might say, well, why'd you do that instead of just brute force compression? And the answer is, well, the brute force compression was sort of viewed as a lower risk, right? We could do it late, it wouldn't change anything, right? Famous last words. So the technique is pretty well known. So we keep the constant term as float, or float 16, and then you, since it contains all the energy, you can use that as an upper bound for the directional term and store that as LDR. Great. So, and I will note that we were okay on perf, and WAD memory was okay. So this was not like a Hail Mary to save the day, but we were trying to get our disk space down pretty aggressively still. So this was going to help with that. So here's a test scene. And crap, it's pretty different. So what happened? So obviously the interpolation is different in this case, right? Because you're essentially multiplying the result of two interpolations rather than interpolating the result of two multiplies. And that was known. We assumed it was going to be negligible. Interestingly enough, like a month after we had scrapped it and moved on, Frostbite published theirs at GDC, where they used this technique exactly, and it worked really well for them. So I assume that's either the resolution, because I think it was light maps, was much higher, or I also suspect that the normal offset meant that we were doing more subtle amounts of self-occlusion, or allowing subtle amounts of self-occlusion due to tuning the normal offset down pretty late in the project in order to get rid of some of those over-occlusion cases that we found to be less than pleasing. So that really couldn't change, so we couldn't really explore fixing it that way. So plan B was, well, maybe we accept a little bit more banding by doing a uniform scale and offset for the whole directional term, and the banding will only be in the directional component, so hopefully less perceptible. And we tested it on a bunch of volumes, and they all seemed to be okay, and the lighters were gracious enough to go back and do a run through of all their levels to make sure that nothing was terribly broken. So thanks for that. And some stats. So these are some hand-wavy numbers because everything is in one big monolithic shader on the reflection pass. So that total thing is like 2 milliseconds. So, and that AO number is, it's sort of like the end of that process of building the AO. That's not the cost of the SSAO. It's sort of the overhead inside. And so somewhere around 3/4 of a millisecond for GI volumes and for cube maps. And obviously it can vary if you had a ton of them on the screen. So this is bake times. Some of the production levels were as little as 30 seconds and up to around 6 minutes, which is quite a big improvement from the Nova pipeline. Variable res, unfortunately, because of that eigen fix up at the end was much slower. This is sort of like a typical worst case. The Lake of Nine, again, being the worst case in the game, was something like 20 minutes. So I think these numbers might include GI volumes that have been abandoned, were left through iteration in game art. So the number may indeed actually be a little smaller, but roughly a third or a quarter were variable res. Most of them were compressed. About 3 gigs in total on the disk, and about a 30% savings due to compression. I'll close with some screenshots from the game. Again. Thanks to Nate and Greg for making me look good up here with all these nice slides. And thanks to Bart and Steven, of course, the Santa Monica rendering team, Aria for her help with the Baker and the Bake Editor, Rupert for the cube maps, Federico with the compression, and obviously the lighting team, who've been gracious and patient through this process, which hasn't always been the smoothest, but I hope the results were worth it. And of course, the obligatory "we're hiring" slide. And I think it's just down to Sean and I today, so definitely go see his talk. All right, that's it. Be careful with my fragile ego with questions.
Hi, quick question.
Yes.
So if I understood you correctly, you were generating the circles by essentially rasterizing orthographic from XYZ directions.
Yes.
Was that configurable, the resolution you used for that to determine like the number of circles, or did you have any
this is something
for tuning that?
I'm sorry?
Did you have any methods for tuning that automatically, or was it just kind of configured manually?
So I don't think this one is the most intuitive. It starts by trying to guess at what would be a decent resolution based on the GI volume resolution.
Okay.
But I don't think the artist found that very intuitive. So I will probably just change that to an explicit what resolution do I want to use for my head texture going forward.
Okay.
Yeah.
Cool. Great talk. Thank you.
Thank you.
Oh, hi there.
Hello.
Thank you for the talk. Were you also able to bake local lights, point lights or omni lights?
Yes, actually, maybe it wasn't obvious in that video where I'm moving the ball around. There's a spotlight on it. So,
Okay,
but yes,
yes.
Omnis also are in there, and there's actually one in that little case. I can go back to it, but yeah, there's.
Yeah, it's fine. Actually, I remember. So yeah, sorry for that.
No, tons of point lights. Yes. Anybody else? Okay. Yeah, sure.
Hi.
Hello.
Great talk. Great
you.
game. Great. Nice looking. Actually, I have a question. What's the data structure that you use in runtime? I didn't really get.
Oh, sorry. They were on the slides, but I didn't actually say it outright, and that was my mistake. It's just 3D textures. They're all filterable 3D textures.
And which 3D texture gets fetched in a shader for given pixel?
Yes, so they're 4, right? So there's RGB for band 0 and then 3 for band 1 each, so 4 in total.
Okay, and the resolution of this 3D texture is 1 meter. What's
sorry?
the resolution of this texture?
It varies between GI volumes based on the, so they author an ideal voxel per meter, and then it's based on the actual extents of the GI volume.
Okay. So just one texture, no hierarchy, nothing.
No, nothing. It's just a series of, no MIP chain if that's the question or anything like that. Yeah.
And what do you do for large levels when you see
So that was
in the distance?
Yeah, so that was the part of the motivation for the variable res is that large levels, if they have large vistas, have large empty spaces. So we're sort of shifting those texels closer to the surfaces, so that in that case, you're largely bound by whatever memory budget you assign to it. So it just does the best it can.
So essentially, you have one big texture.
Yep.
And whatever fits with the resolution you
off the top of my head, I don't remember what the Lake of 9 was our biggest one. I don't remember how big it was. I want to say, yeah, I don't want to speculate, give you the wrong answer.
Thank you. Thank
you. If you want, you can email me and I can look it up.
Sure.
Yeah. Anybody else? Last chance before I escape. Thank you.